Hello and welcome. This is an overview of quadratic functions, and in this lesson you will learn how to sketch and analyze graphs of quadratic functions. Sounds very vague, but let's dive into the specifics right here. Starting with, why do you call it quadratic function? Because a lot of people think of quad as 4, which there is something regarding 4 within it. The origin here, you look at the Latin word quadris, and it means foursquare. And foursquare meaning a square with 4 sides, which is kind of what a square actually is. And quadratus is Latin for squared. And there are other variations of the term, which you can look at here as well. And you can see really where it has to do with square, square, square. Quadratic has to do with squares as well, as squares are something that you multiply by itself, means you're squaring it. Then it is Latin for something of the second power. If something's quadratic, it is of the second power. And so it's not the fourth power, which do not make a mistake with there. That's called a quartic. So quartic is fourth power. Quadratic is second power. Just a nice brief little, I don't know if it's a history lesson, but an origin story there. So here's some of the idea of a quadratic equation or a quadratic function in itself. If we have a, b, and c be real numbers where a is not equal to 0, then we can represent this as a function, and this is called a quadratic function written in standard form. Now the reason why a can't be 0 is because, well, imagine if a is 0. 0 times x squared would be 0, and you'd be left with just bx plus c, or something that is a linear function. The only way that you can be a quadratic function is that your highest degree is of power 2. Regardless of whether or not you actually do have a b or c term, meaning they can be 0, your a value could not. And any of these could be any real number in existence, including irrational numbers. We're mostly going to be looking at these as integers. Every so often we might see a fraction. Rarely will we actually see any square roots like irrational numbers like that. So that's standard form right here, and this is one that I have not been coming across very often. However, I have been coming across a lot of vertex form right here, and we'll be able to differentiate from the two today, what they mean, what they represent, what you can do with them, how you can get from one to the other, etc. So I'm going to jump into this. So these are all different parabolas here. Thank you, Paint. But as I jump over to this next slide here, it's basically going to be a large culmination of different representation of parabolas, either the form and what those things mean, or how they can cross the x-axis, where the vertex can be, how symmetrical they are, etc. So quadratic function, once again, second degree polynomial. All of them generate parabolas. No 3 points are collinear. And I'm going to be hitting on this point later. The standard equation, once again, is ax squared plus bx plus c. This is a simplified form, meaning all like terms are combined. There are no parentheses. It's written in descending order of degree, etc. Ax squared is known as your quadratic term. It's the one with the quadratic in it. Bx is known as the linear term, and c is known as the constant term. Once again, a cannot equal 0. A represents your stretch factor. Stretch factor is for a in your standard equation. It dictates which way it faces, either upward or downward, and it dictates how tall it can be, whether there's something like this or something like this. Despite the fact that they have the same vertex, one might be taller than the other, or maybe another one like that, etc. So you can get different looks based on what your a value is, and it doesn't necessarily affect your vertex. It could, depending on what we're looking at. C is your constant term, and that also means that when x equals 0, all that's left is that value c, which means it also represents your y-intercept. When x is 0, y is c. And that's a fantastic thing to look at. Like, for instance, in this case, this would be 0c, which is the vertex. This here would be 0c, and this here would be 0c in those regards. But in this one on the far right over here, you get an idea where, and I'm jumping into B kind of right here, you get an idea where if your B value is 0, you might recognize here that if you plug in a negative or positive value for x, you just get some value for y that would be equal. Like if I plug in 2 or negative 2 for x, I'll get the same value for y on opposite sides, which means its axis of symmetry is on the y-axis here when there is no B value. So B doesn't actually have, like the number itself, you can use it to calculate the vertex in a way, but the number itself does not represent the vertex, not necessarily at least. But if B is 0, there is something that you can say about your graph. There is no horizontal shift. So this one has a b value that is not 0. This one apparently has a b value that is not 0. This one's b value apparently is 0. So a standard equation can give you the stretch factor. It can give you the y-intercept. It can determine whether or not there is a shift. And you can do some other work to find the x-intercepts rather quickly if it's factorable. There are some good things with this that you can use for graphing this, even if it means it's just a few calculations away. The vertex form, on the other hand, has something that is very calculatable even without a table, provided you know what you're doing with your stuff. H and K are your vertex point. That's the location of your vertex. So right here, for instance, this is your H, comma, K value. So those numbers actually resemble something, and I know that I've been mentioning those things for quite some time now. How do you get the vertex with standard form? You use this thing right here, and I'll be talking about it in a moment. I just wanted to make sure I got vertex located for vertex form to make sure that, hey, it's a lot easier. The a value is the same as the a value in this one. They are both a stretch factor. And what I mean by that is if you have some sort of graph like this one right here, and you wrote the standard form of it or the vertex form of it, you would have the same number here that's right here. If this was a -2, this would be a -2. Whereas the b and the c aren't necessarily anything to do with h and k. You can use them to get to h and k, and you can use h and k to get to b and c, but they aren't necessarily one the same, whereas these a values are exactly the same value themselves. That's really all I have to talk about here because I've already talked about stretch factor. Now getting onto vertex for standard form, let me kind of write it a different way here. Your vertex in standard form, that's standard form, is negative b over 2a represents the x value. And then you substitute your x value into your equation to get the y value. That's what f of negative b over 2a represents. Now, not to get into too deep of a talk here, negative b over 2a resembles something. And I'm not going to do a full algebra proof, but I'll do something through recognition of algebra. Y'all know the quadratic formula? This guy right here. Well, it's saying something to you, and it's actually shouting it at the top of its lungs. This guy right here is called the discriminant. The discriminant is a value such that if it is a perfect positive square root, that means you have rational solutions, 2 of them actually. However, if it's just any positive number, you also know you have 2 rational solutions. This is an example. By solutions, I mean x-intercepts, by the way. This is an example where you have 2 real solutions, 2 real zeros, because your discriminant is positive. Now, why is that the case? Because if you have a positive number here and you take the square root of a positive number, you're left with a positive real number. You can then add or subtract that real number, which means if you add it, you get one solution. If you subtract it, you get another solution. That's why. If it's negative, like this example right here, you will get no real solutions. This is when your discriminant is negative. This is because if it's negative, you're taking the square root of a negative number, which means you get imaginary solutions. You will get 2 of them. You will get 2 imaginary solutions. And I haven't talked with many, if not any videos on imaginary roots just yet. They will be coming into play momentarily, not in this lecture. But 2 imaginary solutions just means it doesn't actually cross the real x-axis. There's some imaginary axis that it's crossing, and yes, there's an actual term for that, meaning imaginary. But it's never actually crossing, and because you're using imaginary values now. It's part of the complex number system, but not the real number system, even when you add real numbers to it. And finally, if the discriminant is 0, what happens is b squared minus 4ac is 0. And this represents just one real solution. Now, the reason for this is because if you take the square root of 0, you get 0. And if you think about if this is 0, this will be negative b plus or minus 0 over 2a, or in other words, negative b over 2a. Now, the only way for your parabola to only cross the x-axis once is if its vertex is on the x-axis. So if its vertex is on the x-axis here, okay, and if the x-intercept for that happens to be negative b over 2a every single time, because that's when you have a discriminant of 0, then your vertex must be at the point negative b over 2a. Now, if that doesn't convince you enough for other points such as this one or this one, let's take a look at it another way. Let's take this and let's split up this denominator so that you have two different fractions, negative b over 2a and square root of b squared minus 4ac over 2a. So this is like a backwards step, because most often we take something that has a common denominator and merge it as 1. But I'm doing it this way instead. What you're taking a look at now, what color have I not used? Let's use some green. What you're taking a look at now is this is the vertex location. And again, if you don't believe me, we're going to go into what the next point is right here. This is the x value of the vertex location. We are going to add this number, and we are going to subtract this number. So we're adding or subtracting the same number, and when you add x values to x or subtract values from x, you are shifting one way or the other in the x direction. If these represent x-intercepts, meaning like this guy and this guy, and if this is your vertex, or if this is the x value of your vertex, this here is square root of b squared minus 4ac over 2a units away from the vertex x value. In other words, I'm adding the square root of b squared minus 4ac over 2a this way. This way, I'm subtracting it. Negative square root of b squared minus 4ac over 2a. Now, it's hard because you're looking at this as this really weird fraction here. I could pretend like this vertex was at the x value of 1, and this was at the x value of 4, and this was at the x value of negative 2. I'm adding 3 this way, and I'm subtracting 3 this way. Where this number is 1, this is plus or minus 3, and that's giving you your two different x-intercepts right there. They have to be the same distance away from the vertex, because that's how symmetry is applied with parabolas, right? They have equidistant points away from this axis of symmetry, which, by the way, I didn't talk about yet right here. Axis of symmetry is at x equals h. But what's the highlight of all this stuff? I can find the x value of my vertex by using negative b over 2a when I'm looking at an equation written in standard form. So this b value does not necessarily represent something on the graph, but I can use it within my vertex equation, as well as this over 2a component right there. Whatever x value I find, say this x value is 1, I plug in 1 to my equation. I take f of 1, and then we get whatever the y value is, and that gives you your vertex. So I'll be talking about that here in this next slide. Let's do some examples here. I'm going to do 2 in standard form, 2 in vertex form. We're just going to see that we can graph them and pull information out of them. Given the following quadratic functions, in this case it's just one function, I think I say that for every one, 1x squared plus 2x minus 8, let's determine the stretch factor and the y-intercept just from the equation alone. Meaning, taking a look at this equation, can we pull out certain information? Yeah, absolutely. Your a value is 1, and your y-intercept is at the point 0, negative 8. Again, when x is 0, you're just left with your constant right there. So we already have some information there, probably not fully graphable yet because we don't know where the vertex is or any other sets of points. So let's compute that vertex and the axis of symmetry, that means axis of symmetry, using x equals negative b over 2a. So what I'm going to do, the x value on my vertex is negative b over 2a, as was established before. B is 2, so I'm going to take negative 2 over 2 times 1. That's negative 2 over 2, which is negative 1. My x value for my vertex is at negative 1, so I know that my axis of symmetry is this line here, x equals negative 1. I know that my axis of symmetry goes through my vertex, and I know that my vertex is somewhere on this line. Okay, let's figure out where that is. Negative 1 for x. What is the y value there? Let's take f of negative 1. Substitute negative 1 in for x in your original equation right here. Whatever y value you get, is the represented y value for your quadratic equation, for your parabola. 1 minus 2 minus 8 is negative 9. So it looks like my vertex is at the point negative 1, negative 9. And that does fit on here. I think that's right down there. So there's my vertex. Okay, compute the x-intercepts by factoring. Now, what we get to do here is, if you're finding the x-intercepts, it's the value of x when y equals 0. So I'm going to substitute 0 for f of x over there. And then I'm going to solve this thing, this quadratic equation, by factoring. It's a factorable quadratic equation. This becomes x plus 4 times x minus 2 equals 0. So if x plus 4 equals 0, then this is zero product property here. And sometimes going past what I've stated in previous videos, it's kind of assumed at some point that if you've gotten this far, then you probably know what you're doing with the equation. If not, there are some other videos you may go back to for that. So I have two x-intercepts here at negative 4, 0, and then 2, 0. And once again, I'm restating kind of what I was saying before about I didn't use quadratic formula here, but if I did, somewhere along the line I'd be saying x equals negative 1 plus or minus 3. Here's negative 1 plus 3. That number's 2. Here's negative 1 minus 3. That's negative 4. That is, once again, that whole negative b over 2a talk and the stuff on the other side, that's what that's having to do with. My b squared minus 4ac over 2a is the number 3. It shows how far away my x-intercepts are from my vertex. Okay, sketch its graph by hand. Now, I have come up with a lot of information here, including the stretch factor, and it's something that I may or may not have to use, even though I could. Let me show you something else we can use. This y-intercept right here. What I've calculated so far is completely without a table. These 4 points right here. I technically used one x value. I had to substitute this value for x to get the value for y for my vertex. But it's a good thing to do anyway, because if you did this just by a table alone, you might not know where to start. Right? Your vertex isn't always right next to the y-axis here. Anyway, so I found these 4 points right here. Now, these 2 points are equidistant from each other, from this height. They're both 3 units away. You must understand there's going to be another point that's 1 unit away at this height right here. There's a corresponding point that's at negative 2, negative 8 with the y-intercept. So as long as the y-intercept is its own unique point that's not the vertex or an x-intercept, you can also reflect across and get that point as well. So 5 points is pretty good for a parabola, but I can get you a few more. If I go over 1, I go up 1 squared. Remember that the stretch factor is 1, so this will just be a normal height for a graph. If I go over 2, I'll go up 2 squared like that. And there's a point right here that also reflects across, of course, just like last time. If I go over 3, I go up 3 squared. Now that's landing on the x-axis right there. Same with this one right here, both landing on the x-axis. Perfect. Keep moving up. If I go over 4, I can go up 4 squared. Negative 9 plus 16 is positive 7. So it looks like it goes up, if I did this right here. And of course, 4 units away, there's another point. So here's an even more complete parabola. But I calculated 5 points without use of a table by gathering information about my parabola. Sometimes you're not so lucky. In other words, sometimes you have a vertex that's on the x-axis. And that's not too bad, but it just means you can only get 1 point out of that information instead of 3. Or sometimes your y-intercept is also your x-intercept, which means you can only get at most 3 points and not 5. This is a special case where you can get more. However, I was also able to do it using my stretch factor. Okay, second example here, given the following quadratic function. F of x equals negative 2x squared plus 8x minus 7. Let's do the exact same stuff. This one's going to be a little, not necessarily harder, just different. Let's determine the stretch factor and y-intercept from the equation. Once again, you can look at these straight up. That's your stretch factor. Perfect. This one right here, our y-intercept now, when x is 0, y is negative 7. So this y-intercept is at 0, negative 7. Now, a lot of people start to get this little inkling that your y-intercept is your vertex, which is definitely not true. But I just mean when I graph this, don't make any assumption that suddenly, oh, the graph just goes like that. It might, but it did make mention that if you have a b value that's not 0, then it will have some sort of horizontal shift. And the more that you play with this stuff, the more that you really do understand how the b value is affected, what it starts to look like. So let's do a little bit more now. Let's compute the vertex and axis of symmetry the same way that I did before. The vertex, the x value, which also helps for your axis of symmetry, is using negative b over 2a. So I have negative b over 2a, which is negative 8, over negative 4, which is positive 2. So your x value is at positive 2 for your vertex, which does mean, and I'll use the line tool this time, your axis of symmetry is on x equals 2. So your vertex is there. Every other point reflects across that, which also does, you can't really see that. Let me make it bigger. Which also does help for a corresponding point already. Remember we talked about y-intercept here. Let me do this with you off the bat. I know there's a point on this parabola that's right here because it's at the same height and it's 2 units away just like the y-intercept was. I already know this information given what I have here. So the x value is 2. The y value for my vertex, let's find f of 2 and determine what that's going to be. Negative 2 times 2 quantity squared plus 8 times 2 minus 7 will give you exactly that. 2 squared is 4 times negative 2 is negative 8 plus 8 times 2 is 16. Negative 8 plus 16 is positive 8 minus 7 is positive 1. So your vertex is at the point 2, 1. Like so. And I can graph that one right there. Okay, the third part of this, compute the x-intercepts by factoring. Now, this one right here, I'm taking a look. I shoot myself in the foot sometimes when I come up with these slides because I mean to do one thing. I don't really put it in play. I don't think this one's factorable. Just taking a look right here. I'm going to go ahead and say it's not. So let's just compute the x-intercepts. Doesn't matter how we do it. I'm going to go ahead and deal with quadratic formula. I think it's really important to talk about that concept I was mentioning before, and I think we can calculate those just fine. That's totally okay. So let's go ahead and compute these x-intercepts here. I have an a value of negative 2, a b value of 8, and a c value of negative 7. So if I compute the discriminant first, I think I can prove to you that it's unfactorable. If I come up with a non-perfect square, then it would be unfactorable. So let's do b squared minus 4ac. Okay, we're going to get 64 minus 8 times 7 is 56. So that's 8. So not a perfect square. 9 is a perfect square, but not 8. So anyway, as I'm doing this problem here, we're going to get x equals minus, negative b, negative 8, plus or minus the square root of b squared minus 4ac all over 2a. This becomes negative 8 plus or minus 2 root 2. That's simplifying that fraction right there over negative 4. And I can simplify this a little bit farther. If I divide by negative 4 here, I'm going to get positive 2. Oh, I can't do negative 4 fully. I can do, these can all divide by 2. So, but negative 2. I can make this a positive 4 plus or minus 1 root 2 all over positive 2, like that. So those are two exact answers right there, but I don't want to keep it like that. I want to show you a little bit more of what I was referring to before. This, if I split up this fraction, this becomes 4 over 2 plus or minus root 2 over 2. Now, 4 over 2 is 2. And plus or minus root 2 over 2, like that. Okay, 2 represents the x value for your vertex. This is x vertex location. This is distance from vertex in the x direction. Plus root 2 over 2, minus root 2 over 2. I'm going to take out the calculator right here, and this will be square root of 2 divided by 2. And it's around 0.7 something, 0.707. There we go, right there. So when I take 2 and I add 0.707, okay, then I'm getting this number here, 2.707. That's one of my x-intercepts. I mean, we know that. We calculated that. But what we did to calculate that, going back up here, is this value here is x equals 2, right there. Well, if I go, about 7/10 of the way over this way, I'm getting this x-intercept right here. I'm adding 0.707. That's that plus b squared minus 4ac over 2a. Minus b squared minus 4ac over 2a is right here. Okay, and that's around the number 1.3. Ish, about 1.293. So those are your two x-intercepts. Again, they're irrational numbers, but it's speaking once again on this concept right here. This is a perfect exact answer, but this does say something. This really does. And if anything, if you have trouble with that, understand the negative b over 2a, the philosophy there. Equidistant units on the x-axis can help represent where that vertex exactly is. So anyway, thank you, calculator. You have done your part. So sketch its graph by hand. Now, we have some points right here, and these aren't the most perfect points. It's better to get ones that cross at integers here. I can get one more set for you guys because I have this a value, the stretch factor of -2. If I go over a full 1, instead of going up 1 squared, I'm going to be going up 1. Take that number, multiply that by -2. Instead, I'll be going down 2. So there's a perfect point that we can cross right there. There's another one on this side as well. And likewise, if I went over 2, I'd be going, instead of going up 2 squared, which is 4, I'm going to multiply it by -2. I'll be going down 8, which does land me on this point, and of course this point as well. So if I finish off this graph now, based on what I have, what I'm given, it's going to look like about that right there. I can't really fit the next set of points, so I think that'll have to do. All right, let's go to vertex form. It actually might be quicker now. We'll see. Determine the stretch factor, vertex, and axis of symmetry from the equation. All right. Well, the stretch factor would hang out on the outside. This value is 1. Looks like we have an a value of 1, just like I was talking about last time. Vertex is at the point, remember, this is x minus h plus k. A better way of saying it is your h value, whatever value you plug in for x to get 0 here, would be your h value. You want x minus h to equal 0 so that you can get your y value of k. So if x plus 2 equals 0, then x must be -2. In other words, h must be -2 in that case. For x, I don't know how to say this. If x is -2, I get 0 into here. Therefore, h is my -2 value. So -2, comma, and that gives you -3 out here. Okay. Axis of symmetry, it's at x equals -2 because it's part of the vertex location. So I already have the vertex. I already have the axis of symmetry. Not too bad. So far, so good. Okay. Compute the y-intercept using x equals 0. So let's take f of 0. And remember, it's not necessarily this -3 out here. This is no longer your constant value in the same sense as your other constant value was. Right? The other one wipes out all my other x terms. This one has an x quantity where you add 2 to it, and it looks like it won't quite be the same. 2 squared is 4. 4 minus 3 is 1. So you have a y-intercept at 0, just the y-intercept at 0, 1, which is right there. Okay? Compute the x-intercepts by the square root principle. Now, I might not have given this term before, but the square root principle is basically saying, all right, let's set this guy equal to 0. We have x plus 2 quantity squared minus 3 equals 0. This is already factored. This is a nice factored form of a perfect square trinomial. I can use that. Okay, I can use that, and I can say if I add 3 to both sides, I'm going to get x plus 2 quantity squared equals 3. And what's great about this is now I can take the square root of both sides. I didn't have to factor, didn't have to use quadratic formula, didn't have to do anything else. I'm taken care of. This is as if I have already done the completing the square process, which is, by the way, something we're about to look into later in this show. So this will be plus or minus square root of 3 for reasons mentioned in previous videos there. If I subtract 2 from both sides, I'll get -2 plus or minus the square root of 3. Now those are two separate values for x-intercepts, and I'm going to go ahead and compute them as best as possible for you right now. by the same understanding. -2 is the vertex location. Plus square root of 3 is some distance out this way. Minus square root of 3 is some distance out this way. Right? We add square root of 3. That's about 1.7. Okay? It's about, there. That x value isn't 1.7, but if I add 1.7 from -2, I get there. Subtract 1.7 from -2, I get over here. All right, so those are your two x-intercepts or thereabouts. All right. Sketch its graph by hand. Let's go ahead and finish this thing off based on what we have and what we can add on to it. Well, we have these two x-intercepts right here. Not perfect points, but I do have a y-intercept that's a perfect point. I can reflect that one across 2 units away. So right there. If I go, this is a stretch factor of 1. If I go over 1, I can go up 1 squared, which is 1. Over 1, go up 1 squared. If I go over 2, up 2 squared, that's these points. And if I go over 3, I go up 3 squared. That's going to be 9. So 6 up from the x-axis is right there. And 3 units away is right there. Looks like enough information there for my graph. Now let's see if I can graph it right. Now my x-intercepts, I didn't really draw the greatest, but they should be going through, right? So it should be doing a little better on that side than I made it, apparently. A little more like that. Can't get my 1.7s exactly right. It's a little more than 1.7, actually. All right, there's its graph by hand there, and the x-intercepts played a small part. But using that stretch factor was still very helpful, as well as any corresponding points. Okay, if I don't want to do all this information for, let's go ahead and take all this following quadratic function, determine the stretch factor, vertex, and axis of symmetry. Of course, that stretch factor is 4. Okay, super tall. Vertex is at -1, -9. Okay, for the same reasons as I kind of stated last time as we were mentioning it. So let's begin this graph here. We're going to start right there. And of course, I could graph it through the rest of this stuff, and that actually might even help me find some of these other answers. But, let's just, let's go with it as we see fit. Compute the y-intercept using x equals 0. No problem. Please do not distribute this 4 into this quantity until you have added 0 and 1 and squared it. 0 plus 1 is 1. 1 squared is 1. 4 times 1 is 4. Minus 9 gives you -5. So your y-intercept is at 0, -5, which is right there. By the way, I haven't mentioned my axis of symmetry, which of course is at x equals -1, as we can see right here. Okay? So I have these points right here, and of course I'm beginning sketching the graph by hand. I can also reflect this point across right here. So you can see this is going to be a significantly taller graph than the others and has everything to do with the stretch factor. Compute the x-intercepts by the square root principle. No problem. Let's go ahead and do the same thing I did last time here. Set f of x equal to 0. Get the x plus 1 squared term all by itself there. So I'm going to add 9 over here. All right. Divide both sides by 4. Now, you might not be too keen on that. It might not be your favorite thing to do here. But good news is this one cleans up okay. If I take the square root of both sides, I'm going to get x plus 1 on the left side. But on the right side, I'm going to get plus or minus, check this out, square root of 9 is 3, square root of 4 is 2. 3 over 2. Hey, not too bad. Subtract 1, I'll get x equals -1 plus or minus 3 over 2. And look, that can be cleaned up a little bit. You can even write 3 over 2 as a decimal if you'd like. Actually, I wouldn't mind doing that. Let's do -1 plus or minus 1.5. Now, once again, this has everything to do with vertex location in the x direction, and then how far you go to the left and right in the x direction to find your x-intercepts, where it crosses the x-axis. But these exact numbers are -2.5, and it looks like positive 0.5. So those, this was clean. These are rational solutions here, and I can graph these pretty well. So -2.5 is right here, and positive 0.5 is right here. Once again, these are revealing this is 1.5 units away and 1.5 units away. I feel like I won't be stressing that anymore now that I've gotten a more tangible version of this answer. And sketch the graph by hand. This is actually already pretty good, these 5 points right here. This is not linear, though. It seems like it. but it still gradually grows. One other set of points I could get here, if I go over 1, I go up 1 squared times 4. We're good there. But if I go over 2, I'll go up 2 squared, which is 4, times 4, which is 16. It's 8, 12, 16. So it's going to be up there. All right, and reflect that point across them right there. It's pretty tall, almost linear-ish, but you might see how these points differentiate. They're not exactly equidistant apart, and it does have a little bit of a parabolic curve. Of course, I can't draw on this thing right here, but there, nice parabola. I think it fits. One thing I haven't really talked about much, I'm going to go ahead and just jump back to it really quickly here. Let's take a look at these 4 graphs, and compared to with this stuff as well. I didn't really mention this a is less than 0 concept. If your a value is negative, your parabola is upside down. If your a value is positive, your parabola is right side up. So looking back at these graphs, positive, up, negative, down, positive, up, and positive, up. So if this was a negative 4, etc., it might change a lot of different things, but in the end, your parabola would go downward. This one in this case obviously did not. Okay, I'm going to go back to these 4 examples here, and I'm going to talk about one other thing that you can do with these. Let's say you were not comfortable with a certain form, and you always had to use the other form. You don't like vertex form, you want standard form. You don't like standard form, you want vertex form. Not a problem. You can do something with that, and in fact, that can help you find any of your other information you were looking for. Like, I have a vertex here and my stretch factor, but I don't have a y-intercept, right? Or maybe I want to find X-intercepts out of this thing and put it in factored form, something like that, right? So we can put it into standard form, and here's what standard form looks like. I said it before, ax squared plus bx plus c. It contains no parentheses. All like terms are combined. Now, you might not see anything to combine at this point, but you will. And terms are written in descending order of degree. So x squared first, x second, constant third. This is quadratic term, linear term, constant term. To apply the conversion, we're going to do the following 3 things. We're going to expand the squared quantity. So I'm going to go ahead and do x plus 2 quantity squared. That becomes x squared plus 4x plus 4. Let's subtract 3. Distribute your stretch factor if a is not equal to 1. In this case, a is equal to 1, so there's nothing to multiply here, right? This is like 1 times this, right? But that's just left with this right here. And then combine any like terms, like the 2 constant terms, right there. So 4 minus 3 is 1. You'll get x squared plus 4x minus 1. There you go. Now, this helps reveal for you your y-intercept. As you can tell, I can now pull out some information that I might not have been able to before. That's at 0, negative 1. Now, this is the same equation as I used back here. That's this one. So there's that point, 0, 1, which is your y-intercept. I don't know why I put negative. Oh, whoopsie, this is a plus 1. My fault. 0, positive 1. So anyway, there's your y-intercept as was over there. So, of course, that matches up. So these are both the same equation. They both represent the same graph, but as you can tell, the numbers mean very, very different things. And they represent different things. It's just coincidence that I have 1, 2, 3, and 4 here. Okay, that's all I was going to do with this problem, and I'm going to do it with the other 3 that I did before. Now, you might be wondering why I'm doing the vertex form ones first. Well, the going from standard to vertex is maybe a little more difficult. It's not just expanding a quadratic here, like this one, a perfect square, x squared plus 2x plus 1 minus 9. We have to do something else, and I'm going to get into that as we get there. Distribute the 4. This one's a little different because this time this form multiplies with all these guys here. Now, I want to make a very important concept out of that. This 4 does multiply with these, which means this number is never truly a 1. It's actually a 4. That's going to be important for when we do completing the square. So here's your equation for this one. All right. Y-intercept is at 0, negative 5. And once again, you can tell the stretch factor is the same right here. 4 and 4. They are both the exact same thing. So we can do that. And I'm just going to kill it right there. Just talk about it like that. But this is also factorable, and I could have solved for my x-intercepts with this thing as it's factorable as well. Okay, let's convert now from standard form to vertex form. Now, vertex form, of course, as we know, looks like this. There's a little more description in it because it's just a little more specific how you have to talk about it. Vertex form I should have written vertex form right here, but vertex form contains a squared quantity, this one right here, where you want to get x and h to be kind of true opposites of each other, meaning if you plugged in a value for h, well, they'd be the same, but if you subtract one from the other, you get 0 out. Okay? In other words, only a 1 for a coefficient in front of x. The stretch factors multiplied outside the squared quantity, not a problem, and any extra constant remainders are added outside the square quantity. So if there's something that doesn't fit within here, we leave it out. So how do we do that? We got to apply the following conversion. Factor out any quadratic coefficients, which there are none, it's just 1, and then complete the square, leaving out the constant term. Now, completing the square, this negative 8 is bothering this x squared and this 2x. It's not helping me complete my square. So I'm going to go ahead and leave that outside of this area here. I'm going to add in a different number that'll give me a perfect square trinomial. This negative 8, you're a bother. Now, whatever I add here, I have to maintain some balance. I'm going to have to subtract on the same side of the equation. Okay? The number that I gather here, I take this 2, and I've done this before. I've done this before in the sense that I've talked about it, but maybe this is a different concept here. Your 2b value is 2. Divide your number by 2, and then square it. Okay? This is the value when you complete the square. The reason I'm mentioning this is because this is what a perfect squared trinomial might look like in this case. Okay? This value is twice the value divided by 2, obviously, and then this value is squared to that. To get from here to here, this is from x plus b quantity squared. I'm sorry for a disjointed lecture on completing the square. I know I have some other videos on it, kind of why I'm mentioning it this way. Anyway, if you expand this perfect squared trinomial, it becomes this. Therefore, to get from this value to this value, you divide this by 2 and you square it. So whatever I add here, I add 1, and here I'm going to subtract 1, and that allows me to keep balance in my f of x equation. Now, I'm not just going to combine all these like terms. The whole point, of course, was to get this perfect squared trinomial right here. This factors into, of course, x plus b quantity squared. If my b value is 1, then this factors into x plus 1 quantity squared. Of course, you can know how to factor that as well. Negative 8 minus 1 is negative 9. So your equation for this one is going to look like that. Now, I didn't really state what else was here, but I did, but I didn't read along. Subtract out whatever was added to complete the square. So I subtracted out whatever was added, and then factor the perfect squared trinomial down to a squared quantity, and then combine like terms outside the quantity. So there you go. Got all that set and taken care of. Now let's confirm this one. If our vertex was at negative 1, negative 9, it looks like we're in business. Let's go over to that equation, that example that I did. Negative 1, negative 9 is a vertex. Yep, looks like it's the same thing. So once again, you can find ways to extract that information by converting from one form to the other. It's useful. This might be more useful to graph. A lot of people don't like to use negative b over 2a for this stuff right here. It's just up to you. Final one, we had this one right here. Let's go ahead and convert this one into vertex form. In order to do this, first thing I have to do is factor out any quadratic coefficients. Now this quadratic coefficient's a negative 2. I'm going to factor it out with just the first two terms here. I am going to leave out the constant term. This guy is going to go off to the side. This is not going to factor out because the only thing that matters is what would go inside my perfect square trinomial when it comes to completing the square. Obviously, that negative 7 won't fit the bill. So this negative 7 is going to hang out here, and whatever I add here, I'm going to subtract here. There's a little wrinkle to what I'm going to subtract, though. I'll make sure to mention it when we get there. Okay, I'm going to take my negative 4. I'm going to divide it by 2. I'm going to square it. This is the value that I'm going to add inside here. Now, I made mention a couple slides ago that remember that this number isn't just a 4. It's negative 2 times 4. Remember, negative 2 multiplies with all three of these guys. I won't actually distribute it. I'm going to leave it factored out. But I'm not going to subtract a 4 here. This number is not 4. This won't balance my equation. What did I add here? I didn't add 4. I added -8. -2 times 4 is -8. So here I have to subtract -8. Okay, it's going to be -2 times 4 right there as well. So that's a kind of tricky part about this. Remember to multiply by any common factors. This common factor of -2 is something I have to multiply this by outside here. So this becomes -2 times, this becomes x minus 2 quantity squared. Now I have a -7, and this, -7 plus 8. -2 times 4 is -8. You're subtracting a -8, which means you're adding. So your final solution for that one is -2 times x minus 2 quantity squared plus 1. It looks like here with the stretch factor of -2, our vertex is at 2, 1. Did we expect that? Well, yes, 2, 1. All right, looks like we're set. We're able to do those problems there. Perfect. So converting to different forms there gives you different information. These both mean the same thing, of course. And as you can see, once again, the A values match up. They should be the exact same in the very end. This one gives you certain information for your graph. This one gives you certain information from your graph. And from these bits of information, you can also calculate others or convert from one to the other. Okay, now we've been graphing equations. Like we've been given the equation and we've been drawing the graph for finding the information. This time we're now going to be creating an equation from information. So, you've done this kind of thing before with linear equations a lot. Not so much from a quadratic equation. Now, here are some facts about quadratic equations and their graphs, and maybe I can draw some things to the side and make sense of what I'm saying. All of them are parabolas, U-shape, which means they all contain a vertex. Hey, there's a vertex. They are all symmetrical across a vertical line of symmetry that goes through the vertex. Perfect. Look at that thing going through the vertex. That goes through the vertex like that, right? That's true. Every single one of them. No 3 points are collinear. Collinear means all in the same line. Like they fall in the same line. Like imagine, there's no constant slope here. So if I pick any 2 points, which of course you can always draw a line through any 2 points, like these two, like that, right? There is no other third point on this line between these two. There is none. They're all non-collinear. And likewise, given any 3 points, a unique parabola can be made. Meaning if you plotted any 3 points on the same graph in the world, I can make a parabola out of it. Might give me a second, but you go like, no, take a look at this one. And I'm like, okay, well, you can go down through there, and it'll come back up, through there, right? There's a parabola that goes through those 3 points. Obviously, just disregard my drawing. But, you're sitting there. Now, they have to be, these should be non-collinear, given any 3 non-collinear points. So you cannot do 3 collinear points. Anyway, you can go like, let's see. I'll stump you this time. You know what I mean? Just, trying to like, haha, what are you going to do there? Like, well, right? So there's perhaps another parabola. So through any 3 non-collinear points, you can always make a parabola. You can also always make a circle, by the way. They will either have 2, 1, or 0 x-intercepts. Now, I mentioned what it looks like to have those 3 and also with the discriminant as well. But given 1 or 2 x-intercepts, there's a multitude of graphs that can be made, given its proper linear factors and any stretch factor. Now, what that means right here is if I have these 2 x-intercepts right here, gee, how many parabolas could you make out of that? Well, here's one, right? Imagine that I drew through that. Here's one. Okay. Here's one, right, that's taller. So you can do any imaginable ones as long as they go through those points. Or just one x-intercept. Here's one. Here's one. You saw it actually on the very first slide, how they kind of there were a bunch of them, right? You can make them taller, like that, whatever. So that's all that's referring to there. Okay. Now, if they have 0 of them, of course, you can make an infinite number as well, but they can also go anywhere you'd like. There's that. there's that, etc. So not as unique in that sense. Using standard, vertex, or factored form, an equation can be generated given any of the information above or a graph depicting said info. Substitute what you know to solve for what you don't know. If you're confused on that, I'm going to do 3 examples with you. 1 using standard form, 1 using vertex form, and 1 using factored form. Actually, I can't guarantee that I use vertex form anytime. Oh, I do. It's the very first one. Knowing the vertex means you know h and k. So if you're creating an equation knowing the vertex in a point here for this guy, if I know what hk is, that means I know my vertex. Knowing a point means you know an x, y value that is a solution to this parabola. So if I know this point A as well, then I can use those for x and y. These 2 points represent exactly one unique quadratic function. In other words, there are no 2 equations that can make any other parabola that has this vertex and goes through this point. None. There's only one. What is left to know is the accompanying stretch factor A. So I know a lot of information about this graph, but I do not know what its stretch factor is. I know that it's negative, but I can solve for it. Solve for A by substituting your known x, y, h, and k values into this vertex form. So the example, find an equation for the quadratic function graphed above, and we're going to write it in vertex form. So I know that my hk values are -2 and a +3, as you can see right there. I have an x value, so this a is crossing at 2, -2. That's where it's crossing through there. So the x value is 2 and the y value is -2. I'm going to go ahead and substitute these 4 things into this equation right here, and that actually will reveal what my a value is as a result of that. So -2 equals a times x minus h squared plus k. Okay. 2 minus -2 is 4. 4 squared is 16. Okay. So subtract 3 from both sides, and I'll get 16a is -5. Therefore, if you divide both sides by 16, a is -5 over 16. Very strange stretch factor there. But hey, it is what it is. You get -5 over 16 as your a value, then you get -5 over 16 as your a value. So what do I write as a final equation because I need to make sure I get it in this form? Well, I'll use my a, h, and k values. Remember, x and y are really just variables. I happened to use one of the variables to solve for it, but it's not a constant parameter like h and k are. Now, h is a -2, so as I subtract -2, it's going to look like addition, and I'll get +3 right there. There's the final equation of that graph, which once again, at least I knew that it was supposed to be negative. I think that was pretty helpful. But yeah, that's all I can really do with that one right there. So that is that answer right there. Knowing the vertex and the point, you can substitute them into there and find your a. Sometimes you can do it just by looking at the graph, but this stretch factor I don't think was clean enough for you to be able to see what happens when you go over 4 and you go down 5. That's going down 5/16 of the number 16, which is 4 squared. It's really tricky that way. That gives you some trouble. Okay, this time let's create an equation knowing its x-intercepts. Now creating an equation, not just the equation. Knowing the x-intercepts means you're knowing its zeros, meaning you're knowing the values of x when y is 0. All right, so we can represent these numbers as linear factors or quantities represented as a product. So I'm going to kind of do this one by one here. I'm going to use the example as I'm going along so you can follow along with what I mean because there's no picture. Now, and I'll draw a picture here though. For an example, write a quadratic equation in standard form that has x-intercepts of 4, 0, and -2, 0. So what I'm looking for is any quadratic equation I can make that's crossing through these 2 points. It doesn't matter which. There's no other specification, which I guess is pretty okay. There is more information that could be given, but, I could make one that, that looks like that, right? But we have to figure out all the other information with it. So I have to write an equation based on it. So what I know is there's x equals -2 and x equals 4. They could be re-represented as linear factors. Now, what I mean as that is if we go backwards, remember if we use zero product property, this would have originally stated x plus 2 equals 0. We would have originally stated here x minus 4 equals 0. That's how we got these zeros out. So if we merge this kind of like zero product property does, we can write these things instead as quantities like this. Okay. So there could have been an equation. This product should be able to equal 0, right? As that is the value for y when looking at these x-intercepts. So right here, we can set it up like this, where if we have these answers, this could have been our original form. And of course, expand from factored form to standard form, x squared minus 4x plus 2x minus 8, and replace the 0 with a y or an f of x. So like f of x equals like that. So here's an example of a quadratic equation that goes through these 2 points. Now this is just one example here. There's another point on top here. Any scalar multiple of this product can qualify as an equation for said graph. There's no one unique equation in this scenario. What do I mean by that? Well, right here my scalar multiple is 1. I'm multiplying these by 1. What if I multiply these by 7? Suddenly my equation is 7x squared minus 14x minus 56. This equation still goes through negative 2 and 4. As you can see, it factors out to this. We can still get these answers. Or it could be, negative 2. And therefore, it's going to be f of x equals negative 2x squared plus 4x plus 16. So all of these go through here. You can create whichever one. I guess the simplest one would be this. But let's say they gave you more information. What if this equation said and has a y-intercept of 16? Well, you'd have to take some more measures to figure out kind of what has to go there. Yeah, that would be a whole different animal at that point. So definitely. It looks like we're doing the right steps there. And finally, creating an equation knowing 3 points. Now, I'm going to be hitting on something called a system, solving for a system of 3 equations here that will not be talked about in any future videos for quite some time. So take what I say as canon and trust that we'll go over it at a different time. You probably have if you've taken an Algebra 2 course, though. So what's going to happen here is you can have, and now we mentioned this before, any 3 nonlinear points that are solutions to a quadratic function. Now, we didn't say can create one unique equation. But remember when I said that you can give me any 3 non-collinear points? You can create a graph out of that. There is only one graph that can be made out of those 3. Okay. Quadratic functions may contain a quadratic, linear, and constant term. 3 terms to be accounted for means a minimum of 3 equations need to be written to solve for A, B, and C when substituting in known x, y values. What the heck does that mean? Well, we have quadratic equations in standard form that looks like this, ax squared plus bx plus c. Well, what if you knew 3 points? What if you knew x was this, y was that, and you knew 3 different ones? We could substitute those for x and y. Now, we wouldn't yet know what A, B, and C were. We'd have to solve for them. But it's impossible to solve for A, B, and C unless you have 3 different representations of it, 3 different equations for it. We're going to be doing exactly that. That's when knowing we have 3 x, y values. The 3 parameters can be solved for using the elimination method for a system of 3 equations, and it can be rewritten into standard form. So let's see what the heck I meant there. Write a quadratic equation in standard form that passes through the points negative 6, 2, negative 2, negative 6, and 2, 6. Got kind of clever with you there, didn't I? A lot of 6s and 2s. All right, these are all x, y values. I'm going to create 3 equations. All of them in this form. I'm actually going to write the y last, though. So this will be one equation is going to be a times negative 6 quantity squared. I'm substituting this negative 6 plus b times negative 6 plus c equals, that is y value is negative 2. There is one of my 3 equations I can represent, and I'm going to, of course, rewrite it so it's a little cleaner. Negative 6 squared is 36. So minus 6b plus c is negative 2. Second equation, substituting in negative 2 for x and negative 6 for y, will look like this. Okay. Now, negative 2 quantity squared is 4, so now I'm going to get 4a minus 2b plus c equals negative 6. And my third equation, I can substitute 2 in for x and 6 in for y. plus b times 2 plus c equals 6. Okay, and I will get, once again, positive 4a. What did I use, green? I'll get 4a plus 2b plus c equals positive 6. So now I have a system of 3 equations here, and depending on how many times you've done something like this, the important part is to get this into a system, one system of 2 equations with 2 variables. So using elimination method, I'm going to choose 2 pairs of equations to eliminate the same variable from. Okay? Now, that might have sounded a little bit confusing, and there are probably a lot of different ways we can go about this. I am going to eliminate my c value. And you can choose whatever you want to eliminate. Looks like these b's would be easy to eliminate. You can do something there. I'm just going to go ahead and eliminate my c value first. No problem. You can do this a lot of different ways. Now, in order to eliminate the c value here, I'm going to have to multiply both of these equations here by -1. Okay, -1, -1, because that'll make my c value negative, and then I can add with this top equation. What I mean by that is if I do 36a minus 6b plus c is -2, and I could have multiplied the top one by -1 as well. If I multiply this one by -1, I get -4a plus 2b minus c equals positive 6. And now when I add down the line here, notice 36a minus 4a is 32a. -6b plus 2b is -4b. c minus c is 0. And -2 plus 6 is 4. All right, well, in this one right here, I get another splendid opportunity where this will be 36a minus 6b plus c equals -2. And then -4a minus 2b, I'm looking at the bottom equation here, multiplied by -1, minus c equals -6. So right here, we're going to go ahead and get 32a minus 8b plus 0, of course, equals -8. All right. Now I'm down to a system of 2 equations with 2 unknowns. I don't know a and b. I still don't know c, but I'm going to use these two, find out what a and b are first to get c afterward. Now you can tell that these ones are kind of like each other, but they're both positive 32a's. Maybe I multiply this one by -1 again. How about that? Because now I'm going to get a -32a to line up with this positive 32a. So 32a minus 4b equals 4. And down here, if I multiply by -1, I get -32a plus 8b equals 8. All right? So now these cancel. I'm left with 4b equals 12. Therefore, b equals 3. Now you're going to watch a lot of trickle up work here. By that I mean I take this b and I substitute it, this 3, I substitute it in for b into any equation that I have with another unknown, like this a right here. So if I take this one right here and substitute 3 in for b, I can solve for a. Minus 4 times 3 equals 4. Okay. I divide by 32, I get a is 1/2. Shame, we get a fraction, but hey, nothing wrong with it, still an answer. So I have a is 1/2, b is 3. I still have to find c, right? Well, I can use any of these 3 original equations right here and do that. I'll do the one with the most positives right here. I feel most comfortable with that. 4a plus 2b plus c equals 6. 4a plus 2b plus c equals 6. Solving for c, half of 4 is 2. 2 times 3 is 6. Okay, so 8 plus c equals 6. Therefore, c equals -2. So I have my 3 values here, 1/2, 3, and -2. And remember what the original quadratic standard form looks like here. It's like this. To get my final solution and see what this final graph's equation would be, it's going to be 1/2 x squared plus 3x minus 2. Now, you can try and plug in some of your values to double check that. Try plugging in -6 and -2 and +2 and see if you get these ones right here. But this becomes the final solution set right there, which of course I could also graph Here, I'll show you on this graphing calculator because I'm jumping into word problems next where I have to use it. Might as well, start working out the kinks. 1/2 is also 0.5 plus 3x, okay, minus 2. Now this graph here, let's see if it goes through. What did I do? One sec. I always have syntax errors. It's something within me here. I might have hit X. Oh, look at this. Caret squared. Here we go. All right, so you get a quadratic equation right there. And you can probably see some of the points. What did we look for? You know what? Let's go straight to the table. But there's the graph. The table, on the other hand, let's see if we get what were they? -6, -2, check. -2, -6, check. And 2, 6, check. And of course, there are a bunch of other points, a lot of which are not integers. Looks like a lot, but they might not fit on a normal graph, or the numbers just might be too big. So that one worked out well. Even though we had a fraction A values, fraction stretch factor. Okay, I'm going to dive in some word problems here. So word problems with these kinds of quadratics, here's what you're kind of going to be asked or what you need to know or do. Like linear models, it's important to understand what the question is asking. Okay, so there's just a big thing there because a lot of people have trouble with word problems because they just see the thing and they're like, I don't know. But so anyway, you got to know what the question's asking for because it helps you know what kind of information you are looking for and what kind of information you also have. But this will help you determine what information you don't know. The things you don't know are called unknowns. Okay, they are unknowns, which means they are like variables. Right? When we create equations or when they model equations, they are things we are not sure of or they can change. And be wary of your units of measurement because when you define a variable or when they define it for you, you have to know that you're answering things in the question in the way they're being asked or that they're lining up properly. And it helps let you know what variables to solve for and what values to substitute in. That's just for all this stuff here. Okay, all quadratic word problems have a natural domain and range, so it's best to try and anticipate what it is beforehand, either to make sense of the problem itself or to double check your work and understand your answers. Reason I say that is because you're going to have a lot of problems. In this case, I'm going to at least do one with you involving like gravity. Okay, and you're talking about something going up and coming down, and it can't go down forever, right? It has to plummet at some point, or it has to even start at some point, and we have to know what that is. So, for example, if the problem is about throwing a ball into the air, then your restrictions probably are the time it takes, or the horizontal distance it covers from the ball's release to its impact with the ground, meaning it won't just go through the ground, right? And also the ground level to the maximum height of the ball. So the ball, it'll come up and come back down, and we got to figure out something with that. So natural domain and range, it's important to know about that because we're going to be asking a lot about mins and maxes for things. If a quadratic word problem is asking about minimizing or maximizing something such as height, cost, profit, or area, it can only occur at the vertex or at an end of the domain. Okay, because think that these things go down forever otherwise or go up forever otherwise. It doesn't actually have a min or max in that case unless you have it cut off at some points here or you're referring to the bottom or top. All right, let's do some word problems. You are standing at the top of a 50-foot cliff. Careful. You throw a ball up into the air and watch it fall. The path it follows is given by y equals -16t squared plus 48t plus 50, where y is the height in feet and t is the time in seconds. Now, as far as this problem goes here, here's my cliff. All right, here's me, or you. And you're 50 feet above the ground. Okay, so this right here is 50. Now, the problem does say that you throw a ball up into the air. You might start thinking, hey, I'm throwing it out this way. Whee! Not necessarily. You could be, but this distance doesn't really matter. There is no variable that refers to distance outward from here, just height. This t is not distance. This is time. So we are going to be looking at a quadratic equation, yes, but you might as well be looking at a ball that you threw straight up into the air and pretend it just, went back down to the ground. So your parabolic curve is not representative of how far away it goes from the cliff, but rather how long it was staying up in the air. So when we graph this thing, and we can graph this one on the graphing calculator together to try and find what the heck we're talking about. This thing here will help us determine where it rises and falls and all that. And for the most part, I'll be doing the calculations by hand, but we can also confirm with this graph. Now, if you're looking at a window, think about what you have here. Plus 50 for a y-intercept. You have to go at least 50 for y. I'll try like 70. Might even have to go higher. I don't know if my x's are right, but one thing that I kind of do know for sure, this negative 10 is kind of irrelevant. All right, think about what the domain's all about. We're going to answer some of these questions. See, looks like I'm not high enough. And as you can see, this room doesn't really matter. I'm just going to go ahead and do 0 for x. I need to go higher. Let's try 100. Y also doesn't matter when it's less than 0 because now I'm below the ground. So, well, it's not bad. I can skinny my x a little bit here, probably to 5. And now I have a graph representing a couple things here. Let's interpret this together. All right. Here I have, well, I don't want to draw it like that. Here I have a parabola where I have a y-intercept of 50. I know that because my x, my t value is 50. When my t value is 0, my y value is 50. I throw a ball up into the air and it comes back down. Now remember, this curve is not representative of the ball going outward. It's the function of time increasing. This is t in seconds. As time goes on, the ball's gravity starts to take place. And a lot of negative 16t squared is going to come up in a lot of physics equations. Meaning, this is a proponent of gravity. They're actually using something involving gravity. And it's about 1, 2, 3, 4, something like that. I don't have it exact here. And I probably won't. It goes out to 4. I don't know. But anyway, so you get your parabolic graph, right? When and where does it reach the maximum height? So when and where? So think about what you're trying to get answered, all right? That was one of the first things I said. Think about what it is you're trying to solve for. This is t, this is y, okay? Now, maximum height. Where does the maximum height occur very specifically or very generally on a parabola? Well, for this upside-down parabola, it's going to be the vertex. So what I'm trying to find is my vertex right here from this equation. And that's my end game. That's what it is I'm going for. So I can do that with the graphing calculator, but if you want to do it by hand or if you had no other choice, we can do one of two ways. We can either solve by completing the square and do that. I'm going to do the negative b over 2a because I'm already in standard form, or do negative b over 2a. So we'll get y equals, and sorry, not y equals. My t value for negative b over 2a will be negative 48 over 2 times negative 16, which is negative 48 over negative 32, which is positive 1.5, right? It's positive 3 over 2. Now, it's good that it's positive because if you can think about what else I talked about with regard to domain, I can't really be less than 0, right? I started my throw 0 seconds in, and I tossed it, and then it landed at some other point. So it's a good thing I at least have a positive number and that it's within 4 units. At least it's making some sense. Plus, this graph kind of starts to agree with that. Now, how do I find the y value? I substitute 1.5 in for t here. So we'll get negative 16 times 1.5 quantity squared plus 48 times 1.5 plus 50. Try and do it without the calculator. I don't know. We'll see how long I can last here. Negative 16 times 2.25 plus 48 times 1.5. Half 48 is 24. So 72 plus 50. Oh, don't make me do this one. 2 1/4. A quarter of 16 is 4. 2 times 16 is 32. 32 plus 4 is 36. This will be a negative 36 plus 72 plus 50. So 36 plus 50 is 86. So to answer both of the questions, because we solved for y, but make sure you answer the question. Indicate units of measurement. When and where? When? At 1.5 seconds after the throw, the ball reaches a maximum height of 86 feet. Okay? So that's what that means there. of 86 feet. There we go. And also to make a little more mention of the equation here, this one's mostly a gravity component. This one is mostly, I'd say, your the strength of your throw, sort of, and this is the height of where you're at. All right. So that answers those questions there. When will it hit the ground is the next question. So what you're looking for is, when will your height be 0? That's what we're looking for. So substitute 0 for y and solve for x. We'll get y equals, negative 16t squared plus 48t plus 50 equals 0. And you solve. We can solve using quadratic formula. I can even reduce these values a little bit if I divide everything by 2. I don't know if it's factorable. I'm not certain here. So negative 8t squared plus 24t plus 25 equals 0. Just to save face, let's test the discriminant and see what kind of thing we're looking for. If it's a perfect square trinomial, I will try and factor with you. So b squared minus 4ac becomes 24 squared minus 4 times negative 8 times 25. So that's 576 plus 30. Let's see. Let's do this. 800. 1376. Even I don't know if that's a perfect square. I don't think it is, but I don't know. All right, so 1376 right here. So when I do quadratic formula, it's going to be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right. So this becomes x equals negative 24 plus or minus. Let's see what this becomes. 1376. Show me. Show me what that is. I have no idea. Square root. Yeah, see, it's nothing great. So I'm just going to go ahead and, I'm just going to kind of round it here. It's about 37.09. Don't worry, when I calculate this, I'll use the exact number, negative 16. Now, by the way, we're going to get two different answers here. There's one where you do negative 24 plus 37.09 over negative 16, and one where you get minus. Now, I want you to think about what the graph looked like here, because only one of our answers is going to be true. There's only one place where this lands on the ground. Now, there is another X-intercept that's down over here somewhere, but that is before we threw the ball, right? When we do quadratic models, there is a very specific domain and range that we have to, be cautious of. And all I'm looking for is the positive one right here. I'm not saying that both can't be positive, but this is the one that I'm looking for. I'm looking for the bigger number, the one that's positive. Now, the number that's going to give me that in this particular case right here, believe it or not, you'd think that it's the one where you add 37.09. It's going to be the one where you subtract it, because this is a negative number down here. So when I do negative minus a number divided by negative, I'll get a positive. So the number that I'm looking for is this one right here. The other one's it's not a value of my concern. It's not one that I'm using. So when will it land? What's my t value? You see, I've been using x. This is actually a t. My t value is approximately going to be, I'm going to go ahead and take negative 24, and I'm going to subtract this value here. So answer like that, and then I'm going to divide this by negative 16. Okay, now this will give me 3.818, so about 3.8 seconds. T is about 3.8. Okay, that's how long it takes for it to hit the ground. So a 50-foot cliff, throw it up in the air, lands down. It seems, I guess it seems reasonable. I don't really know how powerful the throw was, so to speak. But anyway, about 4 seconds there. So if I wanted to use the graphing calculator for all this, just so you're aware, could have actually done this really quickly. If I go to this graph right here, I can find the vertex by going to calc. It's above trace there, and find maximum, where as long as my left bound is to the left of my vertex, my right bound's to the right of it, and I do a nice solid guess out of it, I will land on my desired value. I should be getting, 1.5 comma 86 or something like that? 1.5 comma 86. And again, this calculator has its own rounding issues. I don't know what's going on with it. But it is 1.5 comma 86. Boom, you found it. Maximum height. Still to know you had to find your vertex. The X-Intercept, it's finding a 0. I'm trying to find out. Let's see. I might have to change my window a little bit here. Let's see if I can go off the screen here. That's a left bound. Right bound. I'm going to go past my X-Intercept here and see if that works. Okay, looks like it will. And I hit guess. Give me it. 3.818, comma 0. All right, so we still get the same value out there. So X is really T. And again, answering the question, it takes 3.8 seconds for it to hit the ground after being thrown. All right, so there's modeling that problem there. There's doing a lot with that. Hope that was at least reasonable with regard to what it is that you're doing as you throw the ball. Now, something that some people always say, like, well, you're not, if you're, it says you're standing 50 feet or a cliff that's 50 feet tall, top of a 50-foot cliff. So you're like, well, your arm is right here, so do you go a little taller? You know, it just depends on the problem. If they say your release point is 4 feet above the cliff, yeah, you do go taller. But anyway, they give you the model for the equation, so we're basically following that. The diagram is just a general principle for it. Okay, here's another one in a new type of thing that you're being asked here. Well, you're still being asked for a vertex, but a new type of way it's being asked. A new local musical group is planning to release an album in retail stores next season. So it's the fall now, say during the winter. They hired a data analyst to determine what price in dollars will maximize profits. The analyst came up with the following equation to model the relationship between the price and their profits as follows. So whatever dollar amount they set to sell this thing, right? They're like, oh, it's $10. And who knows? It's $10, right? Some customers will go for that. Right? Some customers will say it's too expensive. There's a sweet spot here. All right? I want you to think about what would happen if I set it at $90. All right? Every time you sell it, you're going to be making some money, but you're not going to be selling quite as, I don't know any CDs that are $90. You're not going to be selling quite as many CDs as you would if you sold it for $10. Likewise, if you sold it for $1 each, you might get a lot of people to buy it. But what if you don't get 10 times as many people to buy it as you would for people that would buy it at $10? Then you're not maximizing your profit, right? If I sold it for a cent, I'm likely not going to profit the same way. So you want to find that thing. Now, how did this guy model this? I don't know. Use demographics and talk to people and whatever else. There are some other things I want to interpret about this thing. That includes the y-intercept and this domain. So based on the analyst's model, what price in dollars should this group sell each CD for in order to maximize profits? So if you think about what's being asked here, they're asking for the X value or the D value of the vertex. Now, just to shake things up, this time I'm going to go ahead and solve by completing the square because I didn't last time. So I'm going to solve this thing by completing the square, and whatever X value or whatever H value I get, like the D value of the vertex, will represent this answer. All right? I'm trying to find what dollar price I get. So if I solve this thing by completing the square and get it into vertex form, once again, that H value will represent what it is I'm looking for. First, I have to factor out a negative 25, and I'll be left with D squared minus, 16, plus blank, minus 375, minus blank. Now remember, this blank here also has to be multiplied by negative 25. Okay? This should say 16D, I'm sorry. Take negative 16 divided by 2, you get negative 8. Square it, you get positive 64. So this will be negative 25 times 64. 64, like so. So P is negative 25 times, this is D minus 8 quantity squared minus 375. Here, let's calculate this one out of here. Save some time. We get negative 375 minus negative, 25 times 64. Okay, 1,225. So plus 1,225. Yes, sir. This is vertex form for this right here. Now, they didn't ask us to put it in vertex form. They asked us to find out what price in dollars should the group sell it at. But this helps answer that, right? Whatever this graph looks like, which this time I did not draw a graph for it, but think about it. It has a vertex at 8, 1225. and it has a y-intercept of 0, negative 375. So it's crossing here, it's doing something way up here, and it's hitting and coming back down like that. Okay, but this point is my vertex right there, 8, 1, 2, 2, 5. And again, what I'm looking at here regarding the graph is this is my dollar amount I should set. This is 8, obviously. And this is the profits I make. So you can see I'm maximizing profits if I set it at $8. What price in dollars should this group sell each CD at? They should sell them at $8 each. Based on this analyst's model, however he figured it out, based on their group or whatever, history, I don't know, he's saying this will maximize your profits, and this is the maximum profit you'll make by selling the CDs. The maximum profit looks like it'll be $1,225. Okay. Now, from there, you could also probably answer something like how many CDs would that be, and stuff like that. It should really say revenue because profit probably includes costs, but this thing probably includes costs with it, right? This minus 375 here. So I wanted to interpret some of this. This negative 375 probably means how much they need to spend to print and distribute the CDs to stores and stuff, right? And then they make some amount of money here, but they spent the 375, which is why this is all they're going to profit. So all this stuff matters with this, right? Their actual revenue was probably just these two combined, and then this is what their cost was. So all that stuff matters with it. Now, domain is greater than or equal to 0 here because you could sell it for free. And notice if you sold it for free, you'd be $375 out. Or you could set it for something larger, but you can't pay the customers, for example, to buy your CD. Well, I guess you could, but don't expect a profit over there by doing it. Now, notice there are parts. Now, your domain could go farther out like this. Like I could set price points at like 40 and such, and this is a realistic one, and it just shows. Well, maybe it is. But you try and make something sell it at this much, you're gonna be losing a lot of money from it. Even if I set it at whatever point this is, let's say it's about 15 or so. All right. If I set it at $15, I might just break even. Just enough customers will buy it so that I made exactly as much as I spent. So all that stuff comes into play. It all very much matters for this kind of word problem, but this is also an upside down graph as a result. Okay, last one. The marketing department of a company estimates that the demand for a product is this right here, where P is the price per unit and X is the number of units. Okay? Don't worry, I'll go over this in a bit. The cost of producing X units is $350,000 plus 30X, that's cost. And the profit for producing and selling X units is this right here. Use a graphing utility to graph the profit function and estimate the number of units that would produce a maximum profit. So this time I'm not going to do completing the square mumbo jumbo, but I will be writing some stuff in here to expand this and then make sense of what it is that we even talked about, because you're probably sitting there going, what? What did we just find? What did we just do? Well, we are looking for maximum profit, so understand we're probably looking for that vertex again. Right? These are all upside down graphs, so to speak. If I do write something for profit here, it is revenue minus cost, which is XP minus C, because they're talking about selling X units. So your revenue is what price point you set your, what is this? A product that you set your product at times the number of products that you sell. That's how much money you make. So that's going to be revenue. So this is X times P. A lot of zeros there. Minus C. So it's going to be this setup. I'm going to, clean this up a little bit. Let's get it more into standard form here. So this is 100x minus 0.0001x squared minus 350,000 plus 30x. Now in standard form, this is negative 0.0001x squared plus 130x minus 350,000. Okay, a couple things with this. Before I can talk about this one right here first, the 350,000. All right, think of this just like the last example that I said there. These are upfront costs. These are things that if you sell 0 units, you're going to be out $350,000 because you didn't sell anything. Or had you not sold anything yet, this is what you're going to start off being out with. it looks like this interpretation is each new unit that you make, you're spending another $30. Cost $30 per unit made on top of the $350,000 you already spent. Here it says that you set your price based on the number of units that you sell. Now that seems a little backwards, right? You're probably saying, wait a minute, didn't we just do the last one where you sell, where you profit based on the price points that you sell, so therefore it's number of units? Sort of. It really depends on what you're talking about. But what economists really tend to say is that changes in production capacity shift the supply curve, and changes in taste shift the demand curve. And these are effectively quantity changes that subsequently affect prices. All right, this makes quantity the independent variable and price the dependent variable. From this perspective, price should be on the vertical axis, right? If you insist that price determines quantity but not the other way around, then you might not understand the effect of weather on agricultural output, right? Also, my guess is that economists measure so much stuff in terms of price that it's convenient to always have the price on the same axis, right? Would you rather prefer to see something on a horizontal axis where it's, something like gas prices are right here, $1, $2, and here are all the different dates that it is, and the gas price changes this way? No, not necessarily. We don't want that. But if it also helps, I looked up something on Google, and I was trying to make more sense of it. And there's this guy named Greg Mankiw or something that he had to say, the way that supply and demand's taught, it makes more sense to have price on the horizontal axis, right? Because the price is viewed as a variable that determines quantity supplied and quantity demanded, and we usually put the dependent variable on the vertical axis. All right, but why is it switched? Mostly because now the early economists were kind of saying that in the very short run, a given quantity of goods was supplied to the market. So I was talking about agriculture, right? Like an agricultural harvest. And the supply curve is then vertical, and the price adjusts to ensure that the quantity demanded equals the exogenous quantity supplied. So in this very short run, the price seems more like the dependent variable. Now, however, the choice of axes is based more on historical convention than logic. But, this one right here, they do give us this set, and we are going to be saying that, okay, this price point is based on kind of what we're anticipating something to be, and let's go ahead and use that just as is. Okay, so there's just a nice little thorough background on that, especially if you were a little lost on that, because, sometimes I kind of am, and I'm taking a look at that and saying, I'm not really sure if that's something that I agree with, but historical things do say that, and sometimes graphically it makes a lot of sense. Anyway, what the price still says, though, is, and I can really only do this with certain X values. You know that this number is incredibly small. Let's say we sold 1,000 units. I'm just giving an example here so that you understand what it is we're looking at. Selling 1,000 units means our price point is and or was likely at, sorry, did I say 1,000? I meant 10,000. 10,000 units would be 10, 100, 1,000, 10,000. We'll be doing 100 minus 1, which is 99. Our price point at 99 suggests that 10,000 units will be sold, or the other way around. If we are trying to sell 10,000 units, we'll set our price point at $99. Okay, so that's kind of the idea behind this thing. So as you increase the amount of customers here, then it's suggested that you lower that price as you go. Like if we want to sell it to this many customers, we will lower our price to this. Okay. Obviously, if you sell it for free, not if you sell it for free. If you want to cater to apparently to 0 customers, you sell it for $100. But if you want to sell it for free, set P equal to 0 and sell for X. Anyway, so here's our curve. Okay, I'm going to use the graphing calculator for this one. And really what I need to do, the biggest challenge for this, you might say, hey, it's easy. I know how to use a graphing calculator. The hardest part about this one is finding this graph. Really making this graph show up on your in your window, because this thing's going to be massive or massively small, but it's going to shoot out very far. You just saw that I get $99 out just for selling. Now that's for price. That's how much I make. But I get $99 out just for selling for 10,000 units. Never mind the fact that this thing's coming into play. I can diminish this a little bit. 45, like that. All right, looks good. Now I finally have something here. Now I got something cooking. All right, let's go and wrap this thing up. Use the graphing utility to graph the profit function and estimate the number of units that would produce a maximum profit. So I'm looking to find the vertex there. That's it. So maximum between here and here, give me, 65,000 for X. So let's see here. We get X, 650,000. And P, profit, is 419,000,000. So this is units. This is dollars. To answer the question, there's a certain, let's see, and this doesn't have price here yet, but there's a certain number of units that I could sell where my profit will be, looks like 41,900,000. So whatever the heck this thing is, man, they're making some money. Now, what price point is that? I'm also curious. We sell 650,000 units for X. That'll determine what kind of price we're doing. Little p is 100 minus 0.0001 times 650,000. Okay. I think we're selling them for, what is that? $35 each? 100 minus 0.0001 times 650,000. Yeah, $35 each. So looks like 100 would have been a little too steep of a price there. So 35 each. And really, I mean, this is the kind of modeling economists do. Now, how do they estimate this stuff? That's a whole nother topic. But modeling it and determining this stuff is exactly what they're looking for. Okay, so wrapping things up there, what was covered was actually quite a bit. But in a nutshell, how to analyze graphs of quadratic functions, meaning certain information based on certain forms, and how to write quadratic function standard form and vertex form, actually, and use the results to sketch graphs of functions, or have the graphs and write it in standard vertex form, and how to use quadratic functions to model and solve real-life problems, like the 3 upside-down ones with vertexes that we just saw before.